To start with, let me remind you what we have been doing last time. So we have the continuous and the discrete Fourier transform relations now. So let me first write down the continuous relations. If you have heard of Fourier series, then you know that when a Fourier series can be written down and when for what type of functions these continuous Fourier transform relations are valid. But they are valid most widely, and they are obviously valid for all the signals, all the time series that one can think about when you are in physics. So these were the continuous cases. And then while talking about the discretization, we said that, so let me write discretization here. So we said that a as a function of t will be now replaced by a with suffix l. So there will be some number of these a's which are measured, and these are nothing but the a sampled at those points which are TL. The sampling interval dt, or whatever we write as dt here as the measure, which I wrote as d mu, that is finite size delta t. So that's my sampling interval. TL is nothing but L times delta t, where L belongs to 0 to n minus 1. Similarly, in the frequency space, we have nu n as n by delta t times n. So small n is again something that goes from minus n by 2 to plus n by 2. And remember, the points at minus n by 2 and plus n by 2 they are related to each other. They are not independent. And the an is the discretized version of the function a, and an is a evaluated at nu n divided by delta t.
So could you again explain the discrete part, because I didn't quite get it. What are we trying to achieve?
See, we have only, so last class, the first slide, if you remember, that we said that we have only a finite number of things that we can represent in a computer. So we have finite precision and a maximum length, right? So if I
Yes.
have to implement the Fourier transform in a computer, I need to have a maximum length, which is, in this case, if you call it t, for t the maximum length is, so I have n samples, so n into delta t actually is the t max, the maximum time I can go up to. And need to have a discretization, the minimum is delta t. Okay. Similarly, in the frequency space, I have nu max, which is n by 2 into delta nu, and delta nu is 1 by delta t into n. 1 by 2 delta t, which I have not written here. So let me write that down as well.
So discrete version is for computation purpose only, right?
This function is for computation purpose only. Yes.
Okay.
Okay. So with these, so this is the continuous version, and the discrete version is. So the discrete versions we wrote in this way. So an is, we wrote it with again making it symmetric. So 1 by root n with both the cases. So this is L equals 0 to n minus 1 AL e to the I 2 pi n times L by capital N. And similarly, AL is 1 by root n again. And so far, whatever we have been written here, so this n goes from minus n by 2 to plus n by 2, and then an. Everything is same, just a minus sign over here. Okay. So this is what we said. But then at the end of the day, we said that, okay, so these two relations are not quite symmetric, the discrete relations, because the summation goes from L equals to 0 to n minus 1 in this case, one case, and it goes from minus n by 2 to plus n by 2 for the other case. So what we do, instead of writing it this way, is that we realize that there is a period in n. So what is the periodicity? The periodicity is that if I have a of minus n, so all the negative values of n, I can map them to a of capital N minus n, because there is a n periodicity. Size or period n. So this also we saw last time. So I can map this. So let's first start by looking at what happens, what is the meaning of this mapping. Okay, so what is actually happening to the data as we are mapping this, because this will be important, and then I will show you a graphic to make the point home. Okay, so let's look at that. So what we have is, so let me write this down, that so our definition of AL was 1 by root n. So I'm writing the same thing again and again, but it is quite useful to understand. Right? And then I do a mapping. The mapping is that A of minus n, I'm mapping that to A of capital N minus n. And that I can do because it is periodic in n. So let's see that what happens then. So what happens then is that I can write this as 1 by root n, n equals to 0 to n minus 1. Okay, which the reason I want to write this as this way is because this is then exactly symmetric to this, the inverse, the actual transform. So where did I have minus? So this was minus, I guess so. Yes. So an is plus. Okay, this was symmetric just from the sign of the exponent. So what is happening here? So let's have a look at it. So remember that small n is an index. So this n is an index per frequency, right? So in the original form, which is this, I have a part of the frequency space which is only available to me. So let's say the 0 is in the in between. So I have the part available from minus nu max to plus nu max. Okay, and then this part I am leveling with integers. So the integers which are the integers are n, the value of the n is minus n by 2 here, 0 here, and plus n by 2 here. And as if you remember, minus n by 2 and plus n by 2 are the same points, right? So because that periodicity is present, I can draw this like in a
Circle.
go ahead. Yes, go ahead.
So circle, right? Or like a loop.
Right. So I can make this as a loop. So you can imagine that the right hand side you bend and bring it like this. So this is your 0. This is n by 2 and also nu max. Let me write this is with the right color, because so this is nu max, and the other side I also bend. So this is minus nu max. And remember that nu max and minus nu max are the same point. Pardon me for the circle not being proper circle. So this is plus n by 2 and this is minus n by 2. They are the same point, and then only I will get total n points. And there is a periodicity of n, which means that if I choose any point here, and if I go with the circle within the circle of n, so if I go around the circle, after n points I will come back there. So if I choose from any point here, so if I call this n equals to 0, my index equals to 0, and then when I come back on the circle, so this point will be again capital N, come back once, this point will be 2n, come back once, this point will be 3n, etc. So this point I can call it 1, or I can also call it n plus 1, I can call it 2n plus 1, etc. So that's what I mean by the periodicity in n. Is this fine? Any question here?
So
It's all right.
so periodicity is V defined, right? Like
No,
what?
it is inherently there. So that we showed last time, that if you try to write down a n plus 1 or n plus l, okay. So if you try to write down a n plus l from this expression, where is the expression? From this expression, then here, because that small n will be capital N plus small n, then that capital N will cancel with the denominator capital N, and what you are left with here is e to the I 2 pi L.
Yes, sir. Yes, sir.
But L is an integer, so I 2 pi is always 1, right? I
Yes,
2
sir.
pi L is always 1. So that's inherently there. So that's a property of the discrete Fourier transform.
Yes, sir.
Okay. So now, so that we understand that there is a periodicity. Now, what we are doing in this shifting is that we are identifying a of minus n as a of n minus 1, which essentially means that we are changing the position. So position of 0. So instead of so here my index is 0 here, right? So in this notation the index is 0 here. Now what we do is that we change the position of the index. So we start from here. This is my index circle. So my index 0 is now here, and my index n minus 1 is there. Okay. And what I do now is I try to fold that. So just like I folded this to a circle, now I try to fold this back to a straight line. And I draw the straight line from 0 to n minus 1 here. Okay. So this is now the way these an numbers are representing, right? After doing this shift in the indexing. So this, if I call it 0 to n minus 1, let's see that what 0 corresponds to, what frequency 0 corresponds to. Well, here nu equals to also 0 at the center, right? So this point is nu equals to 0 still. So this corresponds to nu equals to 0. What does n by 2 corresponds to now?
The new max.
So n by 2 corresponds to nu max. But you see, it also corresponds to minus nu max. Right? This is the same point which is same as nu max and minus nu max. And now, as I go ahead in my indexing, I get minus nu max plus delta nu minus nu max plus 2 delta nu. So here it is minus nu max plus some I delta nu. And the last point here is the point just before 0. So this is delta nu away from 0. So this is minus delta nu. Okay. And then after minus delta nu, go back to nu equals to 0. So the previous point is minus 2 delta nu. So you see how in my index axis, so when I write, if I want to calculate these ans, I get the values numerically a0, a1, a2, a3, a4. So those values are here a0, a1, a2, etc. to an minus 1. So how these values represents different frequencies. Now this is very important to understand because this you have to now somehow get from here to the original thing, because you want to see you want the x-axis to be minus nu max to plus nu max, not some arbitrary way oriented as this is. So this is more, the indexing in this way is more useful because then your forward and inverse transforms can be done with the exact same code. The only difference is plus and minus here, so it's the exact same code, only with that much difference. Otherwise you have to write the codes completely differently. So is this folding of the axis clear? So if you have any question at this point, please make, we'll proceed otherwise.
So you folded the first string, you folded like you made it into a loop and then opened from 0, right?
Right. So I
So you,
started from 0 instead of starting from. So basically what you are doing is, if I see here, so I start from this way, and once I reach the end, then that goes back from that way.
yes, sir.
Okay, so let me show this to you in action, then it will be more clearer for you. So to do that, let me go to the next slide. So if I call that a as a function of t is a Gaussian, so I am not writing with proper normalizations, etc. But the Gaussian is say for example, it's t square by some sigma t square. Then its Fourier transform, which is a nu for us, is also a Gaussian. And this will be by some sigma nu square when sigma t and sigma nu are inversely proportional. Right? So this you all of you should know by now, because you have spent quite some time in physics. So this is one of the important function in physics. And so this all of you should know already, right? So what we will do is, we will try to do the discrete Fourier transform of a function at, which is a Gaussian, and directly look at the discrete Fourier transform. So remember that at, when I write in terms of the discrete samples, this is al, and we'll go from here and we'll write this in terms of an, and then we look at an, but remember that this n has this funny way of arranging the frequencies. So it has 0 to nu max and then minus nu max to minus delta nu. Okay. So somehow we have to understand this, and then if we know, so then what we can do is that we have this index axis, so 0 to n minus 1, and we know that there is a n minus 2 somewhere up to which it is the positive frequency. So I take this part and I take this part separately. So let me so I'm just trying to make sure that which part comes from what side here. And then what I do is I place it. So I take this from here directly and place this back here in the reverse order, which is now this way. And then I will get back my minus nu max to plus nu max. So see, the x-axis is time here, and I have a Gaussian which has a finite width, and so that is represented here. So this is represented with discrete points, but then I have plotted it so it looks quite nice Gaussian. Now what I have done, I have calculated a nu, which is essentially an, what we are talking about, which you can look at in your Jamboard if you wish. And now you see that how this looks like. So it's half of it is here and the half of it is there. Okay. And then I have done the cut pasting. So remember that from here is supposed to be the zero frequency up to n by 2 somewhere here, 512 in this case. You should have the maximum frequency, and that should be equals to the minimum frequency also, minus nu max, and then it goes up to there. So what I have done is that this part I have cut and pasted here, and this part, the half, because this half I have cut and pasted there, and then I get it nicely in my frequency domain. So this is what we were discussing. So this part has to be done for a discrete Fourier transform. This here to here you need to get done to get the x-axis as frequency. This is usually has a name. This is called FF. This is called shift, or Fourier transform shift. So before we proceed, let me make a few important comments here. So I am in the next page of the Jamboard. These are already discussed, but then we will bring up the next thing once we discuss this. The next things will be clear for us. So to bring home the comments, I am writing the relations again. And this, once you see this many times, I guess that this will also be in your heart, close to your heart, and then you'll never forget them. The first important point is that written this way, the Fourier transforms are quite symmetric. The DFT and IDFT are quite symmetric. Why I want to make this point? Because then if I prove anything for the DFT, that will be valid for the IDFT and vice versa. Remember, the first day we make a comment before even if we start the discrete Fourier transform, or the second day, that AT must have a finite support. The function that you are doing the Fourier transform, that must have a finite support. So what does that mean? It means that majority of the contribution, like for Gaussian, it is never zero, right? So Gaussian is zero at x or t tends to infinity. But the majority of the contributions if you go away from the peak of the Gaussian, the contributions from them, the value of the function there is extremely low. It's extremely low. Okay, so it means that majority of the contribution from a range which is say t naught to t naught plus t max. And remember that it not need to be 0 to t max always, because we have the nice shift theorem to save us if it is something else. We can always bring it to 0 to t max, and the extra calculations, the extra corrections that we have to do, we know that how much corrections we have to do and phase part has to be added, so that we can just add by hand after doing the Fourier transform between 0 to t max. Now,
So
yeah,
what do you mean by finite support?
so that's what I explained, right? So the majority of the contribution of the function comes within a certain range in t only. Like Gaussian, if you are from the mean, if you are within -5 to +5 sigma, -5 to +5 of the standard deviation of the Gaussian away from the mean, after, so all the support, all the functional value comes from there. Outside that, it is almost zero. It's, if you assume it to be zero, you will not be doing much else.
So like we can say like bandwidth, right?
Right. So that's where we are going to, but in T it is not bandwidth. Right.
Yes, sir.
So this suggests, so these two, if you now combine 1 and 2, what does it suggest? It tells you that, see, what you see from the 2 is that AT has to have a finite support for the discrete Fourier transform to work. And 1 tells you that IDFT and DFT are quite symmetric. This means that now NU also need to have a finite support. So that is, I can say nu 0 and nu 0 plus some nu max. But so we can always can be mapped to 0 to nu max. So this is because of shift theorem. You can always again map it to 0 to nu max. So which means that in frequency also, if the signal has finite frequency responses within a frequency range, then only DFT will work. So this range is called, as a name, it's called a bandwidth. The range here is 0 to nu max. So the range, the nu max is called the bandwidth. Okay. So nu max is called the bandwidth. These type of signals is also called, these signals are called band limited signals. All the signals that you deal with in your everyday for radio communications are band limited signals, so they only work in a certain frequency range. Otherwise, when you open your mobile phone to talk to me, you may hear some TV channel speaking something else, because their frequencies will bleed to the frequency in which we like to talk. So any question? Okay, so like for example, Gaussian, we saw it's a band limited signal. So that's an example of a band limited signal. So if I had frequency nu and this is a nu, it's only non-zero in a certain region. I mean, it's never zero, but it's very close to zero. You cannot distinguish that from zero. Now, let me pose a question to you, so you should think about it. I will draw two signals here or write down two signals here. So your job is to figure out offline which of these signals you can do Fourier transform, which of these you cannot, and why. So let's say AT is some A0 sine omega t or sine 2 pi nu t, because we are writing in nu. And the other signal that I am writing here is, I'll just draw it, is that it is 0 all the time, but it becomes 1 in between t0 and t0 plus t max. Okay. To look at these, whether these are possible to be represented or done Fourier transform using a computer, or possible to do discrete Fourier transform, you have to remember that both a of t and small a of nu has to have finite support. So a small a of nu has to be band limited, and a of t has to be non-zero only in a given range of t. Okay, so this is what I leave you to think about, and we'll go to the next topic with your permission. So let's go to the final topic in Fourier transform. It's called sampling. So far we have discussed that if I have a discretized signal, how will we do the Fourier transform? We have not asked the question that how do we discretize the signal. So that's what we will talk about now. Okay, so let's say that we have this time signal, time varying signal. So the x-axis is time. I can draw it even further. And y-axis is a as a function of t. And the signal that we are looking at, let's say that this signal is a sine wave. Okay, so let me draw it with a different color. Assume that what I am drawing is a sine wave. All right. Now the question is, how do I get, so what is ALs? How do I get the ALs? Okay. This is a continuous function, right? So how do I get those discrete values? So say I want, so my TL is this point, or let me change the point a little bit. So TL is this point. Okay. So how do I get TL? How do I get AL? So remember, AL is the value of A at TL. Now, if I have a detector which is supposed to make the measurement, there is no way I can detect it at the time t. Every detector works between a time t and t plus delta t. Right? So you cannot just, our eye, you know that it samples every 1 by 12 seconds or so. 1 by 24 seconds or so. So which means I have a range around this at which I detect. So that I can say that actually the signal AL is the average of the signal of the actual signal. Is this clear? So this is what is the discrete version actually is. So you have a small window in time over which whatever the signal comes, your the discrete signal is the average of that. Fine. Any question?
Sir, one doubt, sir.
Yeah.
So we are doing this discretely, but surely, like we studied last in the last part, that there are errors. So how accurate is the discrete part over the continuous?
So
Like,
that's the question you are asking, that if I have these discrete measurements, how accurately we can get the continuous properties of the continuous signal. That's your question, is right?
yes, sir.
So that is the question you are asking right now. But for that, first you have to understand what we mean by a discrete signal. So this is the meaning of a discrete signal.
Yes, sir.
Okay. So now the other question is, how often I should measure this discrete signal. Okay. So let me change this to a different delta, because this we have already used as the time interval at which we will measure discretization interval. So this is a little different thing. This is over which I am averaging. Now I can measure this next one here at this time. So I can measure it here as well, right? So what we call delta t is the time difference between the two samples which are measured. So that is not this small delta t is. So that is for one measurement. Now let us ask the question that how often should I measure this signal? Now we'll so there is a theorem which tells you how often you should measure the signal, and we have already talked about that theorem. So remember that we somewhere we decided that our new max has to be 1 by 2 delta t. So this we said that we will discuss this later, which tells you that delta t has to be 1 by 2 nu max. Nu max is the maximum frequency in your signal, right? We said that somewhere, and that is why is that it comes from a theorem. That's what we'll discuss shortly, or that's what we are discussing right now. So given that we understand the sampling, so let's say that I will do this sampling. So there is a time period of this signal. How much is the time period? That we know that the time period is this much. Right? This is the time period of the signal. All right. So let's say that I measure the signal at the time period. Okay, at the interval of the time period. So would I get the fact that it's a sine wave? So at the interval of the time period means, say I can measure it here. So if I do the first measurement here, the second measurement is here, the third measurement is here, the fourth measurement is here, right? And then if I try to plot this signal, so what I will do is I will just join these measurements. So what do you think? Will you get is there any way of finding out the frequency of this sine wave from these four measurements? No, right? Because you will just get a straight line. Hello?
Yes, sir.
Cannot measure at that interval. So I have to measure at a smaller interval. So I say that I will measure, say here. So which is, how much is from there to there? So this is about 2/3 of the time period apart, right? This is 2/3 of the time period apart exactly. So when is the next measurement? So first half here, 2/3 here, half here, 2/3 here, half here, 2/3 here. Okay. So what will I get now if I add these points by line? The first case I did not get any oscillation at all. Now I get an oscillation. Oscillation means that sometimes it is above 0, sometimes it's less than 0. But what is the time period of this? What is the time period of this oscillation in terms of capital T? Anybody? So it comes back to the same point after how many T's?
3T.
3T, right? So these are the time period of 3T. So I did not, so there is no way I can reconstruct. So if I just do the sampling this way at this interval, so my delta T is like 2/3 of the capital T, then I cannot reconstruct the signal because I will mistake the signal with a frequency which is different than the actual frequency. Now let us see what can be done if we do it at the half of the frequencies. Sorry, half of the time period. Half of the time period is what is given here, because see, nu max, what is the nu of this signal? The nu of this signal is nu, which is 1 by T, and nu max is of course also 1 by T. There is only one frequency. So you see that this I can also write as delta T equals capital T by 2. So you should have half of the time period. So if I do it at the half of the time period, then you suddenly see that you get an oscillation which is exactly at the same frequency as that of the original wave. Okay, so is this point clear? So then I will state the theorem and then we'll call it a day. So this tells you that, so this is called Nyquist Shannon sampling theorem. This tells you, the first thing is that critical sampling interval of a band limited signal is inverse of the twice bandwidth. Critical because if you sample at a faster interval, if I have more points here, there is no harm. So I will get the same signal. So this is basically telling you that delta T has to be less than or equals to 1 by 2 nu max. Okay. And so with critical interval or with critical sampling, a band limited signal can be completely determined. This I cannot prove for you, neither of this, but I think that we have given examples which will take this home. So this second point answers your question that how well should I sample such that I will get the signal accurately. So if you do the critical sampling or better than that, you can actually reconstruct all properties of the signal. So that's a good thing. And the bad thing is that If you don't have a band limited signal, this also tells you, Nyquist Shannon sampling theorem tells you that you cannot reconstruct a signal. Okay. In case if I have a non-band limited signal, and then I can only sample up to a certain time interval, so there will be frequencies which are greater than the nu max. So I will see artifacts of that frequencies, those frequencies excess of nu max, coming into our signal. So those are called aliasing, and you may have heard of aliasing effect at many points. So I will not go through it in detail. I'll just show it here once, that what is the meaning of aliasing. So just bear with me for a second, 1 minute or so. See what happens if I have more than nu max is now in this circle. So if I have something more than nu max, it will try to go around the circle, go past nu max and come here. So this will appear as a frequency which is a negative frequency. So that signal will appear, that frequency will appear as a negative frequency in my discrete Fourier transform. So that will be an artifact which is not wanted. So that's called aliasing. But yeah, so that's what we will discuss today. Questions? Yeah, I'll wait for 5 minutes. If you have any question, you can ask. If you want to leave, you can leave.
Sir, in the first slide, can you explain how you wrote AL?
How did I write AL? Okay. See, what did I say? What is AL? AL is the average of the signal in that region, right?
Yes,
In
sir.
that region. So this is your TL, and it's averaged over a small interval which is delta t.
No, sir, in the first slide.
First slide. Oh, all right. Here,
Yes, sir.
this. So this AL is defined to be A at TL, some representation of the function A at the time TL. That's it. And there we are talking about how that representation is. What is that representation?
Sir, in the left side in discrete, where you wrote AN and AL. Yes, sir.
So this corresponds to AT, and this corresponds to A nu. So this should be nu. Correct that. I didn't get what is your confusion.
Sir, the way you wrote 1 upon root n, this thing. Yes, sir.
This thing.
Yes,
See,
sir.
we saw that we did not prove it, but so when you are doing discrete Fourier transform, here, for example, if I just write it as I omega t, remember that I have a factor of 1 by 2 pi comes in, and then that is divided into the 2. So if I write it in terms of I omega t, so A omega will be 1 by root 2 pi and then the rest of it, and this is also written 1 by root 2 pi and then the rest of it. Similarly, when you do discrete Fourier transform, there is a factor of n that comes in, which is divided into the 2. See, all that we want always, see, one of the transform will have a factor of n, because see, here I have d nu integration, the other one is dt integration. And one of these integrations, when you write, so delta nu or delta t, so that will have a factor of n. Okay.
Okay, yes, sir, got it.
So that factor of n, now what you are doing is you are dividing it into two, 1 by root n, 1 by root n, because what happens is that what you want is that I do a discrete Fourier transform of AL to go to AN, and then I again do a transform to go from AN to AL. I should go get back the same numbers.